So you can actually ask him questions about the exercises. Do you have the exercise sheet? So you will be working on your exercises. You can probably work in this room, in groups or other things. And he will come here and make himself available at 1:30 p.m. if you have any questions. Okay? 그리고 the exercise session will take place at 5 p.m. every day. And you'll be served with pizza and beer. So here I give you Bernd Sturmfels.
Okay, thank you very much. I think I'm okay. Well, thank you very much for the kind welcome and for the great turnout. So I hope it will be an interesting week. So we're going to jump right in. So I said the first lecture today should be at the high school level. The second lecture today should be at the undergraduate level. And then tomorrow we're going to get serious with some graduate mathematics. So don't be too disappointed if the material is too easy today. So in tropical math, we're going to redefine arithmetic. And we're going to say that the sum, the tropical sum of two numbers x and y is the minimum of x and y. The tropical product of two numbers x and y is the classical sum. So let's practice this. So many of the familiar rules of arithmetic hold, such as commutativity, associativity, distributivity. So for instance here, 3 times 4 plus 5. Well, 4 plus 5 is, so that's 3 times 4 plus 3 plus 3 times 5. 3 times 4 is 7. 3 times 5 is 8. You add them up, you get 7. Okay? You could have also done it the other way. 4 plus 5 is 4, plus 3 times 3 is 7. So that's a tropical arithmetic. In tropical math, we have neutral elements for addition and multiplication. Now, to have a neutral element for addition, we have to throw in plus infinity. So sometimes we're going to use plus infinity, so the tropical sum of infinity in any number x is x, right? It's the minimum. And 0 is the multiplicatively neutral element. So 0 times any number is that number. Now the number 1 plays no special role whatsoever in tropical mathematics. So in tropical arithmetic we have addition, we have multiplication. We actually do have division, although we will not need this really. But we don't have subtraction. So there's no tropical subtraction. Well, for instance, if we had tropical subtraction, maybe 7 minus 3, then the equation 3 plus x equals 7 should have a solution. But it doesn't have a solution, right? Because 3 plus x is at most 3, no matter what x is. So there is no meaningful notion of subtraction. Now, elementary school students have to memorize the multiplication table. And they prefer tropical arithmetic to classical arithmetic. So it's easier to memorize the multiplication table in tropical mathematics. And we'll see that many things in mathematics will be easier in the tropical setup. And that's why we're doing it. So we'd like to do something that's easy, especially today. So I've introduced the tropical semi-ring, the real numbers together with plus infinity and the operations addition and multiplication. So many other things that are familiar to you, you can do, such as matrix multiplication, right? So matrix multiplication, so the rows of the left matrix get multiplied with the columns of the right matrix. And here in this example, here's the answer. So the upper left-hand 7 we saw, so 3, 3 against 4, 5, so 3 times 4 is 7, 3 times 5 is 8, you add them up, you get 7. Or maybe the lower right-hand entry, 0 times 1 is 1, 7 times 2 is 9, 1 plus 9 is 1, so we put a 1 in the lower right-hand corner. So matrix operations, vector matrix operations are well defined. And today in the homework, you're going to practice determinants eigenvalues, eigenvectors. So the most important part about these lectures is the homework. Okay, the whole purpose I'm standing here is to help you to do the homework. Occasionally in these lectures I will call on people during the lecture, usually people in the last row. People in the first row will never be called on. People in the last row will be called on. Polynomials you can define. So for instance, here's a quadratic polynomial, x squared plus 1x plus 4. So it's a polynomial in one variable, defined the usual way. But of course, when we evaluate this in classical arithmetic, the sum really is the minimum, right? And then x times x tropically is x plus x classically. So really, if you evaluate this expression f of x, it's the minimum classically of 2 times x, 1 plus x, and 4. So this is a quadratic polynomial. So now you can all take out your tropical graphing calculator, and you can set this as a high school class. So in high school, we have a graphing calculator, and we discuss parabolas, quadratic curves. So let's discuss this quadratic curve. Before we do that, let me mention that this polynomial, of course, factors as a product of 2 linear factors, x plus 1 times x plus 3. You can see, right? So 1 times 3 is 4, and then the cross term is 1, and so on. So this factors as 2 linear factors. So now let's plot the graph. So let me pull out my tropical graphing calculator. Here we go. So first of all, let's look at the range where 4, the minimum, is attained by the number 4. So that happens when x is to the right of 3. So if x is bigger than 3, then this minimum will be attained by the number 4. So all the way on the right side, our graph is given by the constant function 4. Then there's a middle range where x is between 1 and 3. So if x is between 1 and 3, then the minimum will be attained by the middle term. So here's a tiny piece of curve of slope 1. And then finally, if x is less than 1, then the first term, the tropical x squared, will be the dominant term. And so on the left side, there will be a piece of curve of slope, a line of slope 2. So we get the graph of this polynomial is a piecewise linear concave function. And you notice already in the graph that the points x equal 1 and x equal 3, they play a special role. They are the places of discontinuity. That's where the function jumps. And they are exactly the roots of the polynomial. Okay, so that's a polynomial, a quadratic, the graph of a quadratic polynomial in one variable. Oops. No? There we go. Okay, so another thing that you learn in high school, or perhaps in Korea even in middle school, is the quadratic formula. The quadratic formula lets you write the 2 roots of a quadratic polynomial in terms of the coefficients, and plus minus 1 square root blah blah blah. So it's a formula that nobody in my country can remember. Nobody can remember the quadratic formula. That's not so bad, right? Because in tropical mathematics everything is easier. So let's discuss the quadratic formula in tropical math. There are 2 cases. So if classically 2a is less than b, then this quadratic polynomial factors like this. X plus a, so this minus is a classical minus. So x plus a times x plus b minus a. If you multiply this out, right, a times b minus a is the b. And in the other case, you have the double root. You have x plus b over 2, classical half, to the squared. So this is the quadratic formula that takes a quadratic polynomial and factors it as a product of 2 linear factors. Now note in the second case that 2 different polynomials can represent the same function. Those of you who study classical polynomials in finite characteristic know that 2 different polynomials can represent the same function, and the same happens here. So for instance, if a is very, very large, then this function and this function will always be the same function. We will have two different polynomials that can represent the same function. So it's important that we need to distinguish between the function that a polynomial represents and the polynomial itself. Which brings us to homework 1, the fundamental theorem of algebra. So the first homework is for you to prove the fundamental theorem of algebra. So the fundamental theorem of algebra says that every polynomial function f of x of degree n can be written uniquely as the product of n linear polynomials, x plus ci times a global constant. So just like in ordinary mathematics, the fundamental theorem of algebra says that every polynomial has at least one complex root and therefore has n complex roots. We have the same statement in tropical math. So automatically, the tropical semiring, as far as this statement is concerned, behaves like an algebraically closed field. So these ci, they're called the roots of the polynomial. So ci are the roots of the polynomial. So the reason we can call them roots, right, because usually in ordinary math you have a minus here, but in tropical math there is no minus. So therefore we're going to call these ci the roots. So the ci are the breakpoints, are those points where the graph is not linear. Those are the points of discontinuity. Those are the points where the minimum is attained twice. Right? A tropical polynomial is a minimum of a bunch of things, and those are the points where the minimum is attained twice. So let's practice this. So I promised I always first call on people in the last row. So let's see whether we can solve this cubic equation x cubed plus 2x squared plus 6x plus 11. So I claim this has 3 distinct roots by the fundamental theorem. So can somebody tell me a root of this polynomial? Gentleman in pink, you know a root of this polynomial? You make a guess. It's a cubic polynomial and has 3 roots. Pardon me? Minus 2. Well, let's try. So let's plug in minus 2. So to be a root means that the minimum is attained twice. So let's plug in minus 2. So minus 2 cubed is minus 6. Minus 2 times minus 2 times minus 2 is minus 6. 2 times minus 2 squared would be minus 2. They're not the same yet. 6 times minus 2 is plus 4. And 11 is 11. So if I plug in x equals minus 2, I get 4 distinct values. So therefore, x equals minus 2 is not a root of this polynomial. My apologies. The lady in light blue, would you like to suggest a root of this polynomial? Minus 2 is not a root. Five? No? Let's try 5. I heard 5. I heard you say 5. So let's try 5, okay? So 5 cubed would be 15. 2 times 5 squared would be 12. 6 times 5 is 11. And 11 is 11. So you win. 5 is a root, right? If we plug in x equals 5, then the last 2 terms will be equal and less or equal to the others. So x equals 5 is a root. Only 2 more roots to go. 5 is a root. 4 is a root, right? If we plug in 4, then the middle 2 terms will be equal, and they will equal to 10 and less or equal to the other 2. So 5 is a root and 4 is a root. Let me give you a hint. The constant term of a polynomial is the product of the roots. 2, right? So 2 times 4 times 5 is 11, so we found all the roots. Thank you for your participation. So the answer is x is 2, 4, and 5. And you check it, right? You see that when you plug in these 3 values, the minimum is attained twice, and we factored the cubic polynomial into 3 linear factors. Now, I claim this is easier than solving polynomials in ordinary math, so let's compare. Let's see what this means in ordinary classical mathematics. So let's pick a classical polynomial like this. X cubed plus epsilon squared plus times x squared plus epsilon to the 6th x, maybe minus epsilon to the 11. Where epsilon is a small quantity. Okay, so formally for algebraists, I take the rational functions in epsilon and I pass to the algebraic closure. So this polynomial has 3 roots. So what are the roots? Well, that's not so easy. I cannot ask you to do this. In your head, you have to go to Maple or Mathematica. So you go to Maple or Mathematica and you say Puiseux series. And there you go. There are 3 roots. So here's the first root. As x is this power series, has this power series expansion epsilon. That's the second root. And that's the third root. And what I want you to note is that the lowest terms, the exponents of the lowest terms in the classical solution are precisely the tropical roots. So that's going to be the theme of this week, is that tropical mathematics is the logarithm, is the deformed logarithm of classical mathematics. Right? So as we take the lowest terms of the logarithm to base epsilon, we see that the dominant term, epsilon is small, so this is the dominant term. So the tropical roots, they tell us the dominant term in the classical roots. And that will be made precise tomorrow in a statement called the fundamental theorem. Okay, let's move on. Let's talk a little bit about geometry. So plane geometry, but before I do that, this might be a good moment for you to ask me a question. So I asked you a question, so it would only be fair for you to ask me a question. So are there any questions?
So far you gave us 3 categorizations of the roots.
Yes.
So first of all, you said that linear components.
Mm-hmm.
And also you change it to the geometric categorization, say that the points with
yes.
containing. But then I guess it's non-trivial to prove the equivalence.
I see. So let me repeat the question. So I gave you 2 different definitions of a root. So an algebraic definition that says if x plus c appears as a factor, then c is a root. Or a geometric definition, I said it's a point where the curve has a breakpoint, where the minimum is attained twice. And the question, is it hard to prove? Well, you tell me, right? You tell me at 1:30. So this is the first question, is for you to prove the fundamental theorem. And maybe you can decide for yourself whether it's difficult. I think it's not too difficult.
No, I just want to...
Yes, but you need to prove it. It's non-trivial. You need to show something.
And then
yes.
the third one is that
and the third one, it's the image. That's correct. The third one, and again, in one variable, it's not so hard. But really what we want to do in this course, we want to do algebraic geometry in more than one dimension. And then it gets more difficult.
Apparently there is a similarity between the derivation
Yes.
and your...
Absolutely. So tomorrow, lecture 3 is called Fields and Polyhedra. So I will introduce the concept of evaluation tomorrow morning. So today we're going to do high school, elementary school, and tomorrow morning we're going to dive right into fields with non-Archimedean valuations. Question?
Why by any chance called a tropical?
Oh, why is it called tropical? It's a silly reason. So the tropical semiring was used by a French theoretical computer scientists in the early 70s. And they called it tropical because somebody from Brazil had invented it. So it means nothing, it just means the French view of Brazil. Although I have to say, Korea in the summer can be quite a tropical country. Okay, so let's talk about plane geometry. Let's talk about polynomials in 2 variables. So let f of x comma y be a tropical polynomial in 2 variables, x and y. So I would like to define the curve it defines. Now in ordinary math, the curve would be the 0 set, right? Would be f equals 0. But so here we would have to take the plus infinity set. And we could define that, but the correct way is exactly this one. The easiest way is the curve, the tropical curve, t of I, is the set of all points where the minimum in the definition of the function is attained twice. So let's see some examples. So the simplest example of a curve in the plane is a line. So a straight line is the curve defined by a linear polynomial, ax plus by plus c, where a, b, and c are some real constants. Now again, if you're not completely familiar yet with tropical formalism, so in ordinary math, this evaluates as the minimum of a plus x, b plus y, and c. So the curve is the set of all points where either the first two are equal and less or equal to the third, that's this southwestern half ray, or the first equals the last and less or equal to the third, that's this northern half ray, or the third case is these two are equal, less or equal to that, and that's the eastern half ray. Now there's a distinguished point in the middle. There's the point with coordinates x equals c minus a, classical subtraction, and y equals c minus b, and that's where the minimum is attained thrice. By the way, there's seats over here. If you go up there, I will never call on you. So you get a good seat. Okay, so by a straight line in the plane, I will mean any parallel translate of this picture. So it will be a picture that looks like this. It has a northern half ray, an eastern half ray, and a southwestern half ray. Well, let's discuss a few facts about straight lines in the plane. So the first fact is that any 2 points in the plane span a unique line. Indeed, right? So if you draw 2 black points in the plane, there will be a unique line passing through those 2 points. Here are 3 different configurations. Now there's a little bit of fine print. It's not entirely true, actually. It could happen that you're unlucky. If you're unlucky, your 2 points relative to each other could be in eastern, northern, or southwestern position, in which case there are really infinitely many lines passing through these 2 points. But that's the degenerate case, and maybe let's leave that for the afternoon discussion. So if you take 2 general black points in the plane, then there will be a unique line spanned by the 2 points. Now what else is true about points in the points and lines in the plane? Well, the dual statement is true as well, right? Any 2 lines in the plane meet in a unique point. Well, let's see, right? So if you have a black straight line and a blue straight line here, they meet in a unique point. Likewise here, you have 2 straight lines, they meet in a unique point. And again, modulo degenerate configurations. So let's ignore, so if you take 2 general lines in the plane, they will meet in a unique point. So this is the beginning of enumerative algebraic geometry. This is the beginning of what is called intersection theory. 2 lines in the plane always meet in a point. And we're going to have much more to say that, especially in lecture 9 on Friday morning. Well, now that you know that you have points and lines in the plane, you can ask questions, right? You can ask questions about points and lines in the plane. So for instance, you can ask the question, does Pappus' theorem hold tropically? So Pappus' theorem is an example of a classical incidence theorem about points and lines in the plane. And this is a classical picture. So you have these are collinear, and then you form these 3 more intersection points, and then this is an implied line. So Pappus' theorem says if you draw 9 points in the plane and you prescribe 8 collinearities, then the 9th collinearity is implied. Okay, it's a classical plane geometry theorem, the kind of theorems that future high school teachers would learn when they start studying math. Now you can ask, does this theorem hold in tropical geometry, right? We have all the ingredients in place, and there are 2 answers. The first answer is no, and the second answer is yes. Okay? And so we came up with a counterexample in a paper called First Steps in Tropical Geometry, and then a year later a Spanish mathematician came up with the proof, and both of them are correct. It turns out that you have to sharpen the hypotheses a little bit. So you have to be very, very careful the way you actually state the precise wording of Pappus' theorem. What are the hypotheses? And you can either get a no result or yes result. So if you like this kind of, problems about points and closure theorems about points and lines in the plane, this would be a good place to start reading. Okay, but let's move on from lines in the plane to curves of higher degree in the plane. Let's talk about quadratic curves in the plane. Actually, there are already two quadratic curves in the plane, right? One way to make a quadratic curve is to draw two straight lines, right? So this picture is the picture of a quadratic curve, and this is another picture of a quadratic curve. Now, these are degenerate quadratic curves. They are unions of two straight lines. They have a singular point. Here there is a nodal singularity, but they are certainly quadratic curves in the plane. So in general, to speak about quadratic curves in the plane, you take a quadratic polynomial, ax squared plus bxy, cy squared plus dx plus ey plus f. And that's, of course, bad notation. Sorry about that. So a, b, c, d, e, f are some real coefficients. Now we take this quadratic polynomial, we type it into the tropical graphing, 3D graphing calculator, and the 3D graphing calculator will produce for us the graph of this function for any particular values of a, b, c, d, e, and f. And the graph will look like this, right? So for different choices of a, b, c, d, e, f, the quadratic curves will be looking like this. So a quadratic curve has two northern half-rays, two parallel eastern half-rays, and two parallel southwestern half-rays. So any picture like this will be a quadratic curve. And here we had the degenerate case of a quadratic curve, and these pictures are smooth quadratic curves. So let's talk about this a little bit more. So it turns out that this graph is balanced. I'll explain that. And as I said, there are two parallel half-rays in the three distinguished directions, north, southwest, and east. Now, balanced means the following. Suppose you are anywhere on the graph. So let's say we're here on the node. Now, the rays, the edges of this graph, they all have rational slope. So the slopes are rational numbers. So suppose you're anywhere on this curve, and let's declare this to be the origin, right? You look at the edges that emanate from the origin, and you pick the first lattice point in this edge direction. So since the lines have rational slope, as you go along the line, there will be a first lattice point, a first non-zero lattice point, and you mark that lattice point here, here, here. And the condition is that these vectors sum to 0. So this is an equilibrium condition, or zero tension condition, or balancing condition, and that's a characteristic feature. And it turns out for curves in the plane, this characterizes algebraic curves in the plane. So a quadratic curve in the plane is any balanced, in this sense, balanced graph that has three northern half-rays, three eastern half-rays, and three southwestern half-rays. So there we go, and it's balanced everywhere. There it's balanced, there it's balanced, and there it's balanced, right? So that's a characterization of algebraic curves, in this case of degree 2, in the plane. So it's a good idea, if you're new to this, to learn how to draw quadratic curves. So if you didn't bring your tropical graphing calculator today, you might have to do these pictures by hand. So let me teach you how you draw quadratic curves by hand. Okay, so what you do, so step 0, you plot the Newton triangle. So these are the terms, constant term, x, x squared, y, xy, y squared. So these are the monomials that you see in your quadratic polynomial. So next you look at the coefficients, right? There are some coefficients here, a, b, c, d, e, f. And you use these coefficients as heights. You pull out, right? So here you have a, you lift this point to height A over the screen plane in the third dimension. B, C, right? So you move the points out of the screen plane towards you using the heights A, B, C, D, E, F. And then you look at it. You lie in the screen. You look at it from below. And then you see this picture, right? So as you move these points into the third dimension, you take the convex hull. And then this is the lower convex hull. It's the set of faces that you see as you lie in the screen plane. Now this picture is actually the dual picture to the curve we're about to draw. So it turns out that you place a vertex in each of these triangles, and there'll be one vertex for each bounded region, and one edge connected each pair of adjacent regions. And then there's a small thing you need to do. You need to actually rotate by 180 degrees. Okay? Now this rotation is an artifact of the fact that I used the min plus algebra. So I said in defining tropical addition we take the minimum. It would be perfectly fine to take the maximum. So some authors use the maximum, some authors use the minimum. I use the minimum to be consistent with valuation theory. So if you do use the minimum, you have to rotate. So the tropical curve that you get will be the dual graph in precise metric conditions. So you can see that these are two dual graphs. And the coordinates here, so the precise coordinate of that black point is the solution to a linear system of two equations and two unknowns given by these three vertices, right? We want this term to be equal to this term to be equal to that term, right? So this is f plus 2x equals e plus x plus y equals what? C plus y, right? So you solve these equations, and that's the location of this point. So this is duality of planar graphs, and the folks from Pohang, so there's an expert in graph theory, so you can talk to them if you have questions about duality of planar graphs. Okay, let's do another one, right? So here's again the Newton triangle. Now I get some other coefficients, A, B, C, D, E, F. Maybe I get this triangulation. Again, I solve the equations to get the locations of the points, and then I connect according to the dual graph. I rotate by 180 degrees, and there's my tropical quadratic curve, and this was the other tropical quadratic curve. So these are curves in the plane, and you'll have a chance to practice this afternoon. Okay, so here are three facts about plane curves. So we saw earlier that if you have any 2 points in the plane, they span a unique line. And it's fairly easy, to draw that. It takes a little bit more practice to draw the unique quadratic curve passing through 5 points. So if you draw 5 general points in the plane, there will be a unique quadratic curve passing through those 5 points, and that would be exercise 3 on the handout to actually draw this. If you're good, the young people, right, I heard, so Korea has 100% coverage of cell phones, so you probably all have a lot of software, you probably all have Java and all that on your devices. So for the young people, maybe you can take your cell phone this afternoon and build a Java applet on your cell phone that makes this curve, right? So somebody can plop the 5 points onto your cell phone, and then, it makes the curve, and then you can text it to your friends. Okay, but for the older among us, we do this with pencil and paper, right? So we have 5 points in the plane, and we draw the unique quadratic curve through the 5 points. Now, what else? Cubic curves are elliptic curves. So what's an elliptic curve? Well, an easy way to say this, you take a degree 3 cubic curve in the plane that's smooth, and this curve has some very, very special features. It has something called the group law on elliptic curve. These things are very, very useful for cryptography and many other things. And Another way is to think about the Riemann surface, and it's a donut, right? And so it has genus 1, and indeed, smooth cubic curves are elliptic curves. And there's an example of a cubic curve. So how does the tropical graphing calculator draw a cubic curve? Well, you start with the Newton triangle, you subdivide it, you draw the dual graph, and you rotate by 180 degrees, and you get this picture. And you can see visibly, this is a genus 1 graph. There's a unique cycle. So this graph, this one-dimensional polyhedral complex, that's a one-dimensional polyhedral space. Its first homology group has rank 1. So there's the cycle. So there's an elliptic curve. And in the fourth homework this afternoon, you will practice to draw all pictures of smooth cubic curves, or various pictures of smooth cubic curves. What else is true? Bézout's theorem holds, right? So any two plane curves of degree d and e always intersect in d times e points. Well, there's a little bit of discussion about special configurations, but that's always true. So if you have two curves, we saw earlier the case where d and e are 1. If you have two straight lines in the plane, they will always meet in a unique point. But if you have two quadratic curves, they will meet in 4 points. If you have a quadratic curve and a cubic curve, they will meet in 6 points. And I brought a few copies here of this picture. I don't have enough, so maybe pass it around. Some people can keep it. It's a little souvenir. So this is the picture of two quadratic curves meeting in 4 points. So that's a picture for Bézout's theorem. So maybe you can. Some people can keep them, right? So that's two quadratic curves meeting in 4 points. Yes, question.
So in the tropical geometry, there is no need for projective spaces to make this Bézout theorem work?
There is no need for projective space, although we will talk about projective space. Now, the question was, is there a need for projective space to make Bézout's theorem work? The answer is yes and no. It holds without passing to projective space. The way I stated is you don't need projective space, but it's a good idea to use projective space. Now, tropical geometry is a very, very new subject. So the people who work on this, they disagree even on the definitions. So my friends and I, we have heated discussions. What's the definition of projective space? Right? So some people, it's like, is Papa's theorem true or false? Right? We can argue. The same with the definition of projective space. I'm going to give you a working definition of projective space in the second lecture today, projective space being a topic for undergraduate math, but not for high school math. Any other questions? Yes?
Does your plane curves have singularities?
Not this one. That's a smooth. Yeah, the two straight lines that meet in a point, they have a singularity. This one is smooth. You can see, right, if this one were not smooth, so what could happen? You could contract this, right? So you could make a cubic curve, and then the cycle contracts. You could have a rational cubic curve. Okay, so these are a few facts about plane curves. Let's talk a little bit about applied aspects. So I'm very, very interested in computational biology. So I don't know whether anybody came. I know that Kias also has a bit of a life science initiative. So there are many, many applications of tropical and min-plus methods. In these lectures, I will emphasize more, the pure math aspect. So I will not taint you with applications this week. But let me just say a few words about some computational applied aspects of tropical reasoning. So let's talk about matrices and metrics. And again, it's the friends from Postec who are the experts here. So a matrix is a matrix. And we've seen, matrices already on the first slide. You multiply matrices just the ordinary way, rows times columns. I'm going to be interested in matrices of the following form. I'm going to be interested in matrices that have zeros, 0 on the diagonal, and positive or non-negative entries otherwise. Okay? Now those matrices I'm going to identify with weighted graphs. So weighted directed graphs. So here I have a directed graph with forward, backward edges maybe, and every edge has a positive edge weight. So okay, so D12 is the weight of this forward edge, D21 is the weight of the backward edge. So this is a very, very common model. So think about this as the flight network of Korean Airlines. Okay, so Korean Airlines flies to many cities in the world, maybe 4 cities, such as in this example. And this is some measure of distance or cost, right? So D12 is maybe the distance from Seoul to Busan. Okay? Now, the distance could be measured in different things. It could be measured in kilometers, or it could be measured in price. In won, right, for a ticket to fly from one city to another. It could be measured in time, the time it takes you, for a non-stop flight. And so a priori, this need not be a symmetric matrix. So it could be that the flight from one city, from city 1 to city 2, has a different price, right, than the flight from city 2 to city 1. Okay, so think about this as the flight network of some airline, and maybe these are the prices, for a non-stop flight, let's say, or the distance. Okay. So what kind of questions could you ask about this? Well, you may want to find the shortest path from city I to city J. So let's say you want to fly from Busan to Rio de Janeiro on this airline, right? There is no non-stop flight, so you have to connect through different cities, and you want to find the cheapest flight. Well, how do you do this? Well, that's called matrix multiplication. So in your very first discrete math class, you learn about dynamic programming, or Dijkstra's algorithm. And Dijkstra's algorithm says the following. Whoops. I think I lost it. You mind? I think I pressed the wrong button here. Okay, thank you. Okay, so let me state this. So if you form the kth matrix power, so you multiply tropically d times d times d times d, k times, so that's the tropical matrix d to the k, then the entry in row I and column j of that matrix is the length of a shortest path from city I to city j using at most k steps. Now, if in high school or your first year in university, if you've taken a discrete math class, then you know this. This is called Dijkstra's algorithm. So if you know Dijkstra's algorithm, then this is a lemma or proposition. Okay? Now, if you don't know Dijkstra's algorithm, now you do. Right? So the way you calculate the shortest paths in a network is tropical matrix multiplication. And computer scientists call this dynamic programming. So that's nice. So, so if we have a directed graph with n nodes, then to find shortest pairwise distances, well, it's enough to go up to power d to the n, right? So if you have n cities, you don't have to go to a higher power, right? Otherwise, you fly in a circle, which the airlines would like you to do. But, since the costs are, positive here, you don't have to do that as far as cheapest flights are concerned. Okay, so these are matrices and matrix power. So tropical matrix multiplication can be interpreted as finding shortest paths. So let's talk a little bit about metrics. Oops. So such a matrix D is a metric space. Well, I would like it to symmetric. So in a metric, I would like the distance from Seoul to Busan to be equal to the distance from Busan to Seoul. Okay? So that's good. And then also I want d squared to be equal to d. So in this tropical equation, that's called the triangle inequality. The simultaneous holding of all the triangle inequalities can be conveniently written as the equation d squared equals d. Right? So d squared equals d says that for all 3 cities, the triangle inequality holds. That's d squared equals d. So the triangle inequality says, if you want to go from Seoul to Busan, you don't you can't make it shorter by going to Gwangju first, right? You have to, so the distance from I to j is less or equal to the distance from I to k plus the distance from k to j for all I, j, and k, and that's called the triangle inequality, and such a matrix is called a metric, a finite metric space. So the equation that characterizes metrics is d squared equal d. Question? Gentleman back there? You have a comment? Okay, so those are metrics. So now we have matrices with matrix multiplication, and we have metrics. Now I need one more definition. I need the notion of a tree metric. So a tree metric is the following. So suppose we have a tree. So by a tree, I will mean a connected graph without cycles. So a tree is a connected graph without cycles. And suppose each edge in this tree has a length. Well, that's a metric space, right? Because, in fact, any graph is a metric space. But in particular, trees are metric spaces because in a tree, between two leaves of a tree, there's a unique path from any leaf to any other leaf, and that's the distance. So let's see some examples. Oops. So here's an example of a tree metric for n equals 4. Right? So here we have 4 leaves, 1, 2, 3, and 4. These are the leaves of this tree. There are 5 edges, and they have some length. So this edge has length 5, length 6, length 1, length 7, length 2. So my picture is not to scale. Right? So this is a... And then this defines a metric space, right? So the distance from 1 to 2, is a 5 plus 1 plus 7, which is 13. So classical sum. Okay? So that's the... And so on. So the distance from 1 to 3 is 11. So any metric space that you get from a tree like this is called a tree metric. Now here's a question. Is every metric a tree metric? Is every metric a tree metric? So if I start with the metric, can I always find a tree that realizes this metric? Maybe other than Jack, does anybody have an opinion about this? So is every metric a tree metric? Question clear? Now would be a good time to ask. So yes. Yes, every metric? The answer is yes. Okay. Everybody agrees? Every metric is a tree metric?
I think it must have symmetry.
Symmetry. That's true, but so I defined metrics to be symmetric. So D equals D transpose. Okay, so I assume, so I have a metric, it's a symmetric matrix that satisfies the triangle inequalities. Can I find a tree? And was suggested that the answer is yes. No.
We need the tree metric should satisfy certain balancing conditions of the length. Because there is an extra nodes coming in.
Okay, so now we have 2 conflicting opinions. We have a yes opinion and a no opinion. Okay, so everybody's eager for. You have a comment?
You just remove edges, as in if you take wherever you be, and then consider that as a complete graph with those weights, and then just remove all the edges that are useless. Would that not work to give you a tree? Probably not.
So you're sketching a proof? Yeah. Okay, the answer is actually no. So let me give you the no reasoning. So you can see that the answer is no by a dimension count in this example. So let me give you the dimension count. Suppose you have n equals 4, right? So if you have 4 cities, the space of metrics is a polyhedral cone. It's a polyhedral, let me build a polyhedral cone for you. So it's a 6-dimensional polyhedral cone, right? So this is a polyhedral cone. Well, we'll learn all about polyhedra tomorrow morning. So it's a 6-dimensional cone, right? The triangle inequalities, they define the facets of this cone. And it's a full dimensional, so the metrics, the set of metrics is a full dimensional cone inside the 6-dimensional space of matrices with zeros on the diagonal. On the other hand, there's only 5 degrees of freedom in picking a tree metric, right? Because you can see, a tree on 4 leaves has only 5 edges at most. So therefore, just by counting dimensions, right, there are only 5 degrees of freedom to make a tree metric, but there are 6 degrees of freedom to make a metric. So therefore, there should be more metrics than tree metrics. So the answer is no. Not every metric is a tree metric, but biologists care about those that are. So in biology, in molecular biology, so if you open Nature or Science or any other scientific magazine, 98% of the articles are not about astronomy or physics or something. They're about the life sciences. And about half of those papers in Nature or Science will have a phylogenetic tree in them. Right? So trees are ubiquitous data structure in a fast emerging application of mathematics to the life science. So in biology, these leaves are called taxa. So let's think about these as species. Here's the horse, humans, fugu fish, and the mouse, or something, right? So these are biological entities or biological sequences, and most people outside the United States believe that these biological sequences are related by an evolutionary process that would explain these data to be tree-like. Okay? So biologists are very, very interested in those metrics that are actually tree metrics. So let's talk a little bit more about those metrics. And this is a theorem that actually comes from biology. It's not quite true. It was first proved in I think 1971, correct me if I'm wrong, by a person who published this in a journal on mathematical psychology. But let's declare psychology be a life science. So this is a theorem that people know in biology, and it goes as follows. So a metric, D, is a tree metric if and only if satisfies a certain condition, which is known as the 4-point condition. And I'm going to rewrite this condition to be the condition of being contained in a tropical variety, satisfying some tropical equations. And the equations are as follows. So the equations we're going to be interested in are like this. dij, so this is the distance, plus dkl times dkl plus dik times djl plus dil plus djk for any 4 leaves, I, j, k, l, between 1 and to n. And minus d, the classical minus of the given metric, should satisfy all of these quadratic equations tropically. Remind you, satisfying an equation tropically means that the minimum is attained twice. So what we do is we take out our tropical graphing calculator. We have a metric. We pull out our tropical graphing calculator. But now our picture will be in a high-dimensional space. It will be not in the line, not in the plane. It will be in a space of dimension n choose 2. Then we draw, the set of all points where this minimum is attained twice. That's a subset. That's called the space of trees. And then, to be a tree metric means to be in this space of trees. So let me illustrate this theorem in an example. So here is our tree again. So here's a tree with labeled weights on the edges. Here are the distances. So d12 is 1, 3, da-da-da. Distance from 3 to 4 is 9. So what does this say? Well, then we have to pass to minus d, right? So I look at d12 times d34, that's 22. Then this times that, that's 20. And then this times that, that's 22. And then if we negate, the attained twice, right? So this is lying on this tropical hypersurface. So as I said, that's not a new theorem. It's a well-known theorem. And one reference where you can read about this and the geometry of this It's a book we wrote called Algebraic Statistics for Computational Biology, and there's a proof of this theorem and the related discussions. But in the context of this course, this is a theorem that biologists know. But we can reinterpret this theorem here in the context starting tomorrow. We're going to do graduate level algebraic geometry. This is really a statement about algebraic geometry. It says that the space of tree metrics is equal to the tropical Grassmannian, G2n. So the Grassmannian. So you take the Plücker equations that define some variety, algebraic variety. Then there's a piecewise linear space called the tropical Grassmannian. And then one way to think about this theorem is that the space of tree metrics, the kind of metrics that biologists actually care about, those are precisely the points on the tropical Grassmannian. Okay, so I think I should stop now. This goes a little bit, this last green statement goes beyond the high school level I promised for the first lecture today. I just want to give you a glimpse of how the min-plus algebra might relate to applications, say, in computational molecular biology. So everything that you've seen in the lecture this morning appears in a paper called Tropical Mathematics. It's on the archive, and it's also published in a journal. It's a journal of the MAA called the Mathematics Magazine in the most recent issue. Well, if you happen to be in California, if you know somebody who is in California, at the MSRI Institute in Berkeley, there's a research program on tropical geometry in this fall, starting in August. And so what I did this spring to prepare my students at Berkeley for this program, I taught a course, and what's happening here this week is a short version of the same course. So all the course materials are online, including the homework. So this week you're going to get a rerun of the course that I gave to my students in the spring to prepare them for this tropical geometry semester. And that's the end of the first lecture. Thanks. And I think we have time for questions.
In your definition, the tree metric, all nodes have to be at the leaf, right?
That's correct. That's right. So,
That's why his
so
proof fails.
very good. Yes. Very good. So let me repeat what's being said. So the yes argument, so the argument was made that so whether all metrics can be realized by trees, we have to be a little bit careful. What we do is we only take the distances between the leaves. So if you take a general graph, then with the argument that was suggested to know that every metric is of course a graph metric. Every finite metric can be realized by some graph. And, but that's not good enough to realize it as a tree metric because, as was pointed out, we only take the distances from leaf to leaf. So between pairs of taxa, as the biologists would say.